It's my pleasure to introduce Dr. Alex Weibel from Carnegie Mellon University and ATR Interpreting Telephony Research Laboratories, and he will talk on the subject of modular construction of phonetic neural networks.
As this first slide shows, I'm currently at Carnegie Mellon University, but a lot of this work was done in Japan and at ATR Interpreting Telephony Research Laboratories, and we're pursuing this kind of work in both institutions, at CMU and at ATR. I'm going to talk to you about neural networks as applied to phonetic recognition and illustrate some of the advantages as well as the problems that we have to overcome to make this technology really useful for practical applications such as speech recognition. So the first question you may ask is, beyond all this buzzwordiness, why use neural networks, or why are neural networks an interesting approach in the first place? So let me give you a brief overview and introduction over what I see some of the real advantages, why I personally got interested into looking at this technology. One is massive parallelism. It's clearly true that human beings can solve problems like speech recognition or recognizing faces or recognizing objects in the real world instantaneously without much effort. Not only that, we not only recognize what was said when we answer the telephone, but we generally also recognize who the speaker was, what kind of accent the speaker has, emotional state of the speaker, and a host of other issues. Clearly our ancestors could presumably only survive by this ability. They didn't sit in the jungle processing for half an hour when crocodiles arrived. It just all happened instantaneously. And again, we do this by massive parallelism, by having billions of processors cooperating in very intelligent ways to solve these problems. One side aspect of that is the ability of doing massive constraint satisfaction, which gives us the possibility of dealing with ill-defined input. I'm giving you two visual examples here. Most people here in the room will agree that this object on the left here, or set of objects on the left, represents a room with a door and a doorknob and a table, and this might be a picture or a window. On the other side, here on the right, you will see the logo of this company, ATR in Japan. You will be able to read it as A, T, and R, despite the fact that there's nothing in the input really that is a well-defined letter on the right side. And here on the left side, what you really see is a set of squares and rectangles. So how is it that we do this? I claim that we do this mostly by being able to deal with a set of constraints of objects and constraints that are heavily interrelated, and that by the gestalt or the gist or the interaction of all these constraints, we solve complicated tasks. And if we're thinking in terms of serial programs, that is a very difficult thing to do. So one of the things then that people have started doing is building simple computing units, and this is why they are called neural networks, despite the fact that they're really fairly different from actual neurons that we might observe and measure in the brain. Most people currently use simple computing units like this one that I show you, where you have at the input a set of features, F1 through F3. Each feature gets weighted by a weighting function, W1, W2, W3 here, or as many features or incoming inputs you may have. And they get then summed together and passed through a nonlinear decision function, which in the olden days used to be a threshold function. Now most people use a sigmoid function. Now a lot of one such computing unit is then duplicated. There are many of such computing units that can be interconnected And if these weights are set in appropriate ways, then you can construct large, complicated networks that can solve difficult classification problems simply by using a complicated, complex structure of interconnected and interrelated computing units of this nature. Now, if this is true and if we can do that, then this is attractive for hardware implementations because of the uniformity of using large numbers of such simple computing elements. In terms of the kinds of problems, practical cognitive problems that we'd like to solve in a real world, uniformity is another aspect that makes this technology attractive. We would like to have a uniformity of underlying computing structure or computing technology in order to overcome the strict barriers that we currently still have. We have very strict barriers currently between things like acoustic phonetic processing and syntax, or syntax and semantics, or if you want, even speech recognition and visual pattern recognition or character recognition. We know that human beings have a lot more crossover, that priming occurs across these modalities. And having some uniformity in the underlying computing is attractive for that reason. Now, if you look far back into our past of computer science, you may discover in pattern recognition books a beast called perceptrons, which may tell you that these ideas aren't strictly new, and people have tinkered with them, and somehow they sort of have fallen by the wayside and have recently become really interesting again and buzzwordy again. And I wanted to just quickly explain to you what explains some of these changes over time. In the past, people have tinkered with these simple computing elements that I showed you one off, where you have these a set of incoming features. They are weighted and they are summed and passed through a decision function. Now, that was all nice, and there were actually learning algorithms that could automatically come up with a reasonable set of weights in order to use a perceptron, such simple computing unit, for classification problems. Now, many people at the time discovered, however, that one such unit is actually very limited. And Minsky and Papert wrote at the time this book, Perceptrons, which also showed, among other things, that a perceptron cannot even solve a simple problem like finding the right output behavior of an XOR function. I've drawn you here this example of an XOR function in feature space where you have 0 and 1 as feature 1 and 0 and 1 as feature 2. And you can see that a linear decision element, such as the perceptron, cannot properly derive the XOR function or produce the XOR function output, simply because there's no way of essentially drawing a line in this feature space that separates the two classes, the two output categories. So people got discouraged by that and sort of stopped working on this mostly. And it's only recently that new learning algorithms have come around that have caused this renewed interest in neural networks. So the good news there is that we have the same idea before, the simple computing units, but we now have actually learning algorithms that can deal with many layers and many interconnections and can therefore construct arbitrary nonlinear decision surfaces, even if they are very, if their structure is rather complex. The optimization there is always performed in view of the global goal. So even in the days of the perceptron, people had put together individual decision units, but they were mostly trained in a locally optimized fashion. They were always trained individually, and then people tried to put them together, and that's problematic. So with these new learning algorithms, people train the individual units in view of how they can contribute to producing the optimal overall result. Some other aspects that were very exciting when people started working with them is that after learning was done and these algorithms would approach a reasonable solution, you can study what has actually happened to the internal, what we call hidden units, hidden neurons that are unspecified neurons that are allowed to learn any abstractions as they may like. And people have now gone and studied what these hidden units have actually learned and found that they learn very reasonable, very interesting properties of a task. And that is, again, a desirable aspect of this approach. Now, the bad news for speech is that most of the initial attempts were incapable of dealing with this property of time. Speech is a time-varying signal, and really what you need to have in time is the ability of capturing the dynamics. Speech is like a signature in feature space, where the actual momentary local state of the articulators is not so much important. It's not as important as the actual movement, the dynamics, the direction that your articulators take. If you pronounce a vowel in continuous speech, you may actually never reach the targets of a proper vowel, but your articulators motion in that direction, and that motion actually gives away what you intend to say. So what we need to do is be able to capture the temporal dynamics, the temporal properties of speech, and we need to do so independent of segmentation. We heard in the previous talk that that is one of the things that Markov models have been applied rather successfully to. The idea is that you'd like to recognize events in speech independently of where and when they occur. You don't want to have to pre-segment the signal before you can start doing recognition, because you're piling two problematic tasks on top of each other. Another aspect that's difficult with neural networks is this problem of computation time. As networks grow larger and larger to larger and larger problems, more and more computation is required, and some ideas are necessary to see how these problems can be overcome so we can apply them to large problems. So we then went off and introduced a what we call a time delay neural network, and this is again work that happened in collaboration between CMU and this lab in Japan. We start off again with multi-layer neural network. That's a network with several layers of such computing units, and by doing so we can represent arbitrary nonlinear decision surfaces. Some of the other properties is that we already start off with a neural network that is designed appropriate for the task. So rather than sitting there trying to force a general purpose neural network to solve all our problems, we already limit it. Why waste time? Build some suitable amount of knowledge into the architecture appropriately, and we can minimize the learning time and the amount of training data required and get good results in the end. Now, these problems of time we have attacked by coming up with a time delay arrangement to the simple computing elements, and I will show you how that looks in a second. And translation invariant learning is the other property that we have implemented in this particular network. Here what we mean by translation invariant learning is that the hidden units of the network are trained in such a fashion that they learn acoustic phonetic features independent of the precise location in time. So think of them as little cells that sit there and watch the input as it passes by. And as soon as the right set of events occur, they start firing and pass their firing pattern on to whoever is listening in the next level up. And by doing that, we gain that freedom from precise time alignment or segmentation that we'd like to have. This is how one such time delay neural network unit looks like. As you can see, it is very similar to the old perceptron in that there is an incoming feature that is weighted by a weighting coefficient and passed through a summation function, and then through a nonlinear decision function, which again in our case we use a sigmoid function. Now, in addition to these straight features that are weighted by a weighting coefficient, we also have delayed versions of the same feature. So here this feature is passed through a delay unit D1 up through Dn possible delays. By doing so, what one such unit can do is not only look at the current value of an incoming feature, but also its past history, up to n past delay snapshots, if you like. And in doing so, what a unit can learn to do. That was all very encouraging, and we now went a step beyond that and said, okay, let's apply all these techniques and these ideas that we have and actually construct a larger phonetic recognition neural network. And we've done this on the example of an all-consonant network, a network that tries to recognize any consonant in this Japanese database. And this is a overview. I'm afraid that's probably not in your proceedings. This is a fairly recent result and recent slide that I produced. What you see here is all the hidden units as they were developed from the various sub-component networks. So we have a BDG network, a PTK network, a nasal network, a fricative network, and all the other classes that I showed you before. In addition, we have here a network that is a class discriminator. So very much like the voiced-unvoiced network, we have here a network that classifies between the different consonant classes. We've only experimented so far with a very simple initial way of merging them. We're merging them only at the very highest level. And there are a number of additional experiments that we haven't really tried. And I've described the techniques that we've developed on BDG PTK, and a whole set of them has not been tried on this larger problem yet. So this is just the very first crack at this problem, and this is what you get just from doing that. So what you see here is again, the recognition performance of all the individual subcategory phonetic classes discrimination networks. And the last entry here is the performance of the consonant class distinction network. And by retraining these higher layers to do a simple combination of these subnetworks, we got an all-consonant network that performed at 95% recognition accuracy. Now, if we open up all the connections to do some additional all-net fine-tuning, as I described before, this recognition accuracy goes up to 95.9%. And I don't think that result is in the copy of your proceeding of your slides that you have in your proceedings. So it's a fairly recent thing we've tried, and I expect further additional application of the techniques that I described before to give some additional improvements. Again, we've compared that with the various hidden Markov models that we were experimenting with in Japan. The hidden Markov model that I described earlier did 83.6%, and after now in the last year and a half or 2 years, adding a number of additional techniques that are, as I said, very successful, like differential coefficients, I think some duration control. There were some different labeling schemes to separate out word initial phonemes from word middle phonemes and so forth. That recognition accuracy was improved to 92.7%. So what you can see is still the performance here is respectable for something that is just the first pass at solving this problem in this way. So let me conclude on what we have learned here. We view these techniques that are described as steps for the design of larger neural-based, neural-motivated systems, if you like. What we want to do is clearly go towards all these extensions and see how these neural network connectionist techniques can be applied to the overall speech recognition problem. Whether there might be possibilities for hybrid solutions, merging them with techniques that are useful in the hidden Markov models, for the hidden Markov models, as well as other recognition strategies. For this particular, what we've learned particularly here on the problem of designing large phonetic recognition networks are the following set of techniques. First of all, it appears that using the learned hidden structure of previously trained network is a win. We can already work with previous notions and attack larger problems with them. Modularity, therefore, seems to be a viable strategy for building large neural networks. Modularity, I should caution everyone, again applied in an intelligent fashion. You can't simply plug these things one into another. You have to have some ways of merging them. And these ways of merging we've described. They include using class discriminatory features, connectionist glue. They also, I have not talked very much about selective learning. What we mean by that is learning only subportions of a larger network in selective ways. And I did mention some results of all-net fine-tuning, which means taking a large modularly constructed network and allowing it to get used to, for the subcomponents to get used to each other some more. An aspect here also is the idea of incremental learning. In doing all this, we also have a way of training networks in an incremental way rather than having to be training the whole network all in one swoop. So we believe that some of these techniques and ideas are useful in going for the large problems such as speaker independence or building word-level models and models of that are useful for continuous speech, speaker-independent speech understanding eventually. And that concludes my talk.